4.5 billion years ago, our planet was a molten ball of rock and metal spinning in the cosmic void. But the Earth we know today, with its 7 distinct continents, is not how it has always been. 335 million years ago, all the land on Earth was united in one massive supercontinent called Pangaea. This is the story of that ancient world, and how its formation and destruction shaped everything we see today. To understand Pangaea, we must first journey back to the very beginning of continental formation, over 4 billion years ago during the Archean Eon. The first continental crust began to form as lighter materials rose from the molten interior, creating the foundations of what would become our continents. These early landmasses, called cratons, became the stable cores around which future continents would grow. But the Earth's surface was never static. The theory of plate tectonics tells us that the outer shell of our planet consists of massive plates that constantly move and interact. When these plates collide, they create mountain ranges, volcanic activity, and gradually push continents together. When they pull apart, they create new ocean basins and separate land masses that were once connected. This process, known as the Wilson cycle, describes how ocean basins open and close over hundreds of millions of years, driving the supercontinent cycle. Throughout Earth's history, continents have repeatedly assembled into supercontinents and then broken apart in a predictable cycle, lasting approximately 400 to 600 million years. Before Pangaea, there was Rodinia, a supercontinent that formed around 1 billion years ago and began breaking apart 600 million years later. As Rodinia broke apart, its fragments drifted across the globe, setting the stage for the next phase of the supercontinent cycle. These continental fragments were surrounded by Pangaea, a vast global ocean that covered most of the planet's surface. But the same tectonic forces that broke Rodinia apart would eventually drive these scattered continents back together, beginning the assembly of Pangaea. The assembly of Pangaea began during the Paleozoic era, approximately 400 million years ago, as the scattered continents slowly converged. Laurentia, the ancient core of North America, was one of the first major players in this continental collision. Baltica, containing much of what would become Northern Europe, drifted toward Laurentia from the east. When these two continents collided around 400 million years ago, they created the Caledonian Mountains, remnants of which can still be seen in Scotland and Norway today. The microcontinent Avalonia, carrying parts of what would become eastern North America and western Europe, was caught between these colliding giants. Meanwhile, in the southern hemisphere, the massive supercontinent Gondwana had already formed, containing what would become South America, Africa, Antarctica, Australia, and India. As Gondwana drifted northward, it collided with the combined Laurentia-Baltica landmass in a massive mountain-building event called the Hercynian orogeny, creating ranges across what is now Central Europe. By 335 million years ago, these collisions had created Pangaea, a supercontinent that contained virtually all of Earth's landmass. Pangaea stretched from the North Pole to the South Pole, forming a massive C-shaped landmass that dominated one side of the planet. Within its embrace lay the Tethys Sea, a large ocean embayment that would play a crucial role in the supercontinent's eventual breakup. On the opposite side of the planet, the vast Pangaea Ocean covered nearly half of Earth's surface, making our world fundamentally different from today. This supercontinent was enormous, covering about 30% of Earth's surface area. The formation of Pangaea created some of the most spectacular mountain ranges in Earth's history, including the ancient Appalachian Mountains, which once rivaled the modern Himalayas in height. The Ural Mountains formed as the boundary between the European and Asian portions of the supercontinent, marking the suture zone where ancient continents collided. The Alleghenian orogeny completed the assembly of eastern North America, creating a continuous mountain chain that stretched for thousands of kilometers. Simultaneously, the Variscan orogeny was building mountain ranges across what would become Central and Southern Europe, from Britain to the Czech Republic. Over the millions of years that followed, these towering peaks were gradually worn down by erosion, their sediments spreading across the supercontinent. Pangaea's formation was accompanied by intense volcanic activity as the Earth's crust adjusted to this new continental configuration. Deep within the Earth, mantle plumes began to rise beneath the supercontinent, creating hotspots that would eventually contribute to its destruction. One of the most significant volcanic events occurred near the end of Pangaea's existence with the formation of the Siberian Traps, a massive volcanic province that would have profound consequences for life on Earth. Later, the Central Atlantic magmatic province would form as Pangaea began its breakup, creating one of the largest igneous provinces in Earth's history. The massive size of Pangaea created internal stress patterns that began to fracture the supercontinent from within. Early rift systems began to develop, particularly along what would eventually become the Atlantic Ocean basin as the supercontinent started to stretch and thin. During the Triassic period, these rift systems became more pronounced, creating the first signs that Pangaea's days as a unified landmass were numbered. Pangaea's massive size created extreme climate conditions unlike anything seen on Earth today, with vast interior regions experiencing severe continental climate. The supercontinent's geography created massive monsoon patterns, with intense seasonal rainfall in some regions and prolonged droughts in others. Much of Pangaea's interior became vast desert, as these regions were too far from the ocean to receive adequate moisture. During the Permian period, Pangaea supported a wide range of environments from lush coastal regions to arid interior deserts. The unified landmass of Pangaea allowed for unprecedented biological exchange, as early reptiles evolved and diversified across the supercontinent without oceanic barriers. Today we find identical fossil species on continents separated by vast oceans, providing compelling evidence for Pangaea's existence. The Glossopteris plant, found in rocks across South America, Africa, Antarctica, Australia, and India, could never have crossed the modern Atlantic or Indian Oceans. Similarly, Lystrosaurus, a mammal-like reptile, has been discovered in Antarctica, South Africa, and India, continents now separated by thousands of kilometers of ocean. Mesosaurus, an early aquatic reptile, is found in both South America and Africa, but nowhere else, indicating these continents were once connected. The therapsids, ancestors of modern mammals, evolved and spread across Pangaea, taking advantage of the connected landmass to colonize diverse environments. By the end of the Permian period, Pangaea supported complex ecosystems with diverse plant and animal communities, but this biological richness was about to face its greatest challenge. 252 million years ago, the Permian-Triassic extinction event, also known as the Great Dying, eliminated over 90% of marine species and 70% of terrestrial species. This catastrophe was likely triggered by the massive Siberian Traps volcanic eruptions, which released enormous amounts of carbon dioxide and toxic gases into the atmosphere. The resulting global warming and ocean acidification created conditions so extreme that life on Pangaea nearly came to an end. In the aftermath of this extinction, Pangaea's landscapes were largely barren, setting the stage for new forms of life to evolve and diversify. During the Triassic period, life slowly recovered, and new groups of organisms began to evolve and spread across the supercontinent. By the late Triassic period, around 200 million years ago, rift systems began to develop across Pangaea, as internal stresses started to tear the supercontinent apart. The most significant of these rifts developed along what would become the Central Atlantic, beginning the separation of North America from Africa. The sedimentary rocks of the Newark supergroup, found along the eastern United States, preserve evidence of these early rift valleys and their unique ecosystems. These rift valleys became evolutionary laboratories where early dinosaurs evolved and diversified, taking advantage of new ecological niches. During the Jurassic period, rifting gave way to seafloor spreading, and the first true Atlantic Ocean began to form, permanently separating the northern and southern portions of Pangaea. As the Atlantic Ocean widened, Pangaea split into two major supercontinents: Laurasia in the north, containing North America, Europe, and Asia, and Gondwana in the south. Laurasia consisted of what would become North America, Europe, and most of Asia, connected by land bridges that allowed continued biological exchange. Gondwana remained more intact for a longer period, maintaining connections between South America, Africa, Antarctica, Australia, and India, well into the Mesozoic era. The Tethys Sea expanded and evolved, becoming a major oceanic realm that influenced global climate and ocean circulation patterns. During the Cretaceous period, the breakup accelerated as the South Atlantic Ocean began to open, separating South America from Africa. The evidence for Pangaea's existence was first compiled by Alfred Wegener in the early 20th century. Wegener noticed that the edges of continents, particularly South America and Africa, fit together like pieces of a jigsaw puzzle. He also observed that rock formations and mountain ranges on opposite sides of the Atlantic Ocean matched perfectly, as if they had once been continuous. Perhaps most compelling was the evidence of ancient glaciation found across southern continents that are now in tropical regions. indicating they were once positioned near the South Pole. Modern paleomagnetic evidence, which preserves the orientation of ancient magnetic fields in rocks, provides definitive proof of continental movement and Pangaea's existence. Pangaea's massive size fundamentally altered global climate systems, creating circulation patterns completely different from those of today. The supercontinent's interior experienced extreme continental climate, with scorching summers and frigid winters due to its distance from moderating oceanic influences. Seasonal monsoons of unprecedented scale developed, bringing intense rainfall to some regions while leaving others in perpetual drought. The supercontinent's configuration dramatically altered ocean circulation, affecting heat distribution and creating new patterns of warm and cold ocean currents. During certain periods, Pangaea's climate supported extensive ice sheets, particularly when parts of the supercontinent were positioned over the poles. Vast desert regions expanded across Pangaea's interior, creating some of the most extensive arid environments in Earth's history. In contrast, Pangaea's coastal regions supported diverse environments, from tropical reefs to temperate forests. Massive river systems developed to drain the supercontinent's interior, creating some of the largest drainage basins in Earth's history. These rivers deposited enormous amounts of sediment around Pangaea's margins, creating thick sedimentary sequences that we can study today. The Jurassic period, beginning 200 million years ago, marked the beginning of Pangaea's dramatic breakup. The central Atlantic Ocean began to open, creating the first permanent separation between North America and Africa as new oceanic crust formed along the mid-Atlantic ridge. Simultaneously, the Gulf of Mexico began to form as North America rotated counterclockwise away from South America. The Tethys Sea continued to evolve and expand, becoming a major oceanic realm that influenced global climate and marine ecosystems. As the continents separated, dinosaur populations became isolated, leading to distinct evolutionary paths on different land masses. During the Cretaceous period, the breakup of Pangaea accelerated dramatically, reshaping the planet's geography. The South Atlantic Ocean began to open around 130 million years ago, finally separating South America from Africa. India broke away from Gondwana and began its remarkable journey northward toward Asia, traveling at the geologically rapid rate of up to 20 centimeters per year. Antarctica became increasingly isolated at the South Pole, setting the stage for its eventual glaciation. Australia separated from Antarctica and began its own northward journey, carrying unique flora and fauna into isolation. The North Atlantic continued to widen, pushing Europe and North America further apart, and creating the ocean basin we know today. The Cenozoic era, beginning 66 million years ago, witnessed the final fragmentation of Pangaea's remnants. India's collision with Asia around 50 million years ago created the Himalayan mountains, the highest mountain range on Earth, and continues to push these peaks higher today. The Alpine orogeny created mountain ranges across southern Europe as Africa continued to push northward against the European plate. The Red Sea began to form as Africa and Arabia started to separate, representing one of the most recent examples of continental rifting. By 20 million years ago, the continents had reached approximately their modern positions, though they continue to move today. Today, the continents continue to drift at rates of centimeters per year, following the same tectonic processes that created and destroyed Pangaea. Modern GPS technology allows us to measure these movements with incredible precision, confirming that continental drift continues today. The Atlantic Ocean continues to widen by about 2 to 3 centimeters per year, pushing the Americas further from Europe and Africa. Conversely, the Pacific Ocean is gradually shrinking as the surrounding plates converge, with the Pacific Plate being subducted beneath adjacent continents. The East African Rift System provides a modern example of continental breakup in action, as Africa slowly splits apart along this active rift zone. Based on current drift rates, scientists can project where the continents will be millions of years in the future. Computer models predict that in approximately 250 million years, the continents will once again assemble into a supercontinent tentatively named Pangaea Proxima. Alternative models suggest the formation of Amasia, where the continents would converge around the North Pole rather than along the equator. Regardless of the exact configuration, the supercontinent cycle will continue, driven by the same tectonic forces that created and destroyed Pangaea. The breakup of Pangaea had profound consequences for the evolution of life, as isolated continents became natural laboratories for independent evolutionary experiments. The isolation of Australia allowed marsupials to evolve and diversify without competition from placental mammals, creating unique ecosystems found nowhere else on Earth. Madagascar's early separation from Africa led to the evolution of unique species like lemurs and baobab trees, found nowhere else in the world. South America's isolation for much of the Cenozoic era allowed for the evolution of unique mammalian fauna, including giant ground sloths and terror birds. When North and South America reconnected 3 million years ago, the Great American Interchange allowed species to migrate between continents, dramatically altering ecosystems on both landmasses. Modern patterns of biodiversity across the globe still reflect the legacy of Pangaea's breakup and the subsequent isolation of continental fragments. Modern scientists use sophisticated techniques to study Pangaea, including paleomagnetic analysis that reveals the ancient positions of continents. Fossil excavations continue to provide new evidence for Pangaea, as scientists discover species that lived across the ancient supercontinent. Seismic tomography allows scientists to peer deep into the Earth, revealing the remnants of ancient subduction zones and the scars left by Pangaea's assembly. Sophisticated computer models help scientists reconstruct the exact positions of continents throughout Earth's history and predict future movements. Ocean drilling projects provide direct evidence of seafloor spreading and continental breakup by sampling the oceanic crust formed as Pangaea separated. New fossil discoveries continue to shed light on life during Pangaea's existence, revealing the complex ecosystems that thrived on the ancient supercontinent. Technological advances including satellite monitoring and GPS tracking allow scientists to measure continental drift in real time with unprecedented precision. Understanding Pangaea requires collaboration between geologists, paleontologists, climatologists, and biologists, each contributing unique perspectives to this ancient puzzle. Every major ocean basin on Earth today was created by the breakup of Pangaea, fundamentally shaping the geography of our modern world. The continental shelves that surround modern continents formed as the edges of Pangaea were stretched and thinned during the breakup process. Many of the world's islands formed either as small continental fragments left behind during breakup, or through volcanic activity along new plate boundaries. Modern mountain ranges from the Himalayas to the Andes formed as a direct consequence of the tectonic forces unleashed by Pangaea's breakup. Modern biogeographic patterns still reflect the ancient connections that existed when Pangaea was intact, with related species found on continents now separated by vast oceans. The isolation of continental fragments led to the evolution of endemic species found nowhere else on Earth, from Australia's kangaroos to Madagascar's lemurs. Conversely, similar environments on separated continents sometimes produced remarkably similar organisms through convergent evolution, demonstrating the power of environmental pressures. Modern conservation efforts must account for this biogeographic legacy, protecting unique evolutionary lineages that developed in isolation over millions of years. The modern thermohaline circulation system, which regulates global climate, was established only after Pangaea's breakup created the ocean basins necessary for these currents. Modern monsoon systems, particularly the Asian monsoon, were fundamentally altered by the collision of India with Asia and the resulting Himalayan uplift. The formation of modern polar ice sheets was only possible because of the continental configurations established after Pangaea's breakup, particularly Antarctica's position over the South Pole. Major ocean current systems like the Gulf Stream formed only after continental separation created the ocean basins and geographic configurations necessary for these currents. Regional climate patterns around the world continue to be influenced by the topographic and oceanic features created during and after Pangaea's existence. The global carbon cycle evolved significantly as Pangaea broke apart, with new ocean basins and continental configurations altering the storage and cycling of carbon. Continental breakup affected global weathering patterns, as increased continental margins and mountain building altered the chemical weathering of rocks. The formation of new ocean basins fundamentally altered global nutrient cycling, affecting marine productivity and the evolution of ocean ecosystems. Understanding Pangaea's history has practical applications today, as geologists use this knowledge to locate mineral deposits and understand their formation. Oil and gas exploration relies heavily on understanding the sedimentary basins created during Pangaea's breakup, particularly along continental margins. Knowledge of tectonic processes that created and destroyed Pangaea helps scientists understand modern earthquake patterns and volcanic activity. Climate scientists use models that incorporate continental drift to understand long-term climate change and predict future environmental conditions. Modern satellite systems continuously monitor continental movement, providing real-time data on the ongoing processes that once created Pangaea. Museums around the world use Pangaea reconstructions to educate the public about Earth's dynamic history and the evidence for continental drift. Modern educational technology allows students and the public to virtually explore Pangaea and witness its formation and breakup. Understanding Pangaea and continental drift has become fundamental to scientific literacy, helping people understand the dynamic nature of our planet. As we look at our planet today, with its familiar arrangement of 7 continents and 5 oceans, it's remarkable to consider that this configuration is temporary. Pangaea reminds us that Earth operates on timescales almost incomprehensible to human experience, where continents drift like ships across the planet's surface. The same processes that created and destroyed Pangaea continue today, slowly but inexorably reshaping our planet's surface. In the distant future, our descendants may look back at our current continental arrangement with the same wonder that we view Pangaea today. Our understanding of Pangaea represents one of the greatest triumphs of scientific reasoning, piecing together evidence from across the globe to reveal Earth's hidden history. Pangaea teaches us that our planet is not a static stage for life but a dynamic, ever-changing world where the very ground beneath our feet is constantly in motion. The story of Pangaea is ultimately the story of our planet itself, a reminder of the incredible forces that have shaped the world we call home.